When the Xbox adaptive controller first came out, there were two ways to get an analog joystick into it. And the first, there were X1 and X2 ports on the back that used 4-pole TRRS plugs to connect to. The other method was USB. Now, the TRRS is pure analog, and again, it goes through the X1, X2, also through the two triggers, but it requires an analog stick with two potentiometers. This is a standard replacement ALP stick, and I've wired it to a plug and a jack so that I could plug it into the back. So this is relatively straightforward. There's no microcontroller or anything else. But I don't really build these because the USB side of things on the Xbox adaptive controller really suits a lot of needs, and it suits the needs of digital devices, devices that aren't simple XY devices like this joystick. Well, what happened? I've put this aside, and I haven't really looked at X1, X2 in a long while because I haven't had to. But in December, Sony came up with their PlayStation Access controller, which is a neat little controller for adaptive gaming, which is great. The downside is it only has one analog joystick. Why these companies only put one analog joystick on these devices, I do not know. Probably the more concerning thing for me is that there's no USB. So none of my USB joysticks work with it. In the meantime, I've taken a look at designs that I do have that would work pure analog, and I've migrated those. So I have versions of the Palm and the Joy-Con style that are available for the PlayStation, because the PlayStation uses TRRS jacks, 4-pole cables. So I was able to migrate a couple of ones, and it does end up being simpler. It's more actually work wiring it for me, but there's no microcontroller inside. But you lose a lot. You lose the ability to use any pure digital devices like the GlidePoint, like the Nunchucks, like touchpads, like mice, on and on and on. All of those specific devices you're locked out of. It's just not going to happen. So that's why I dove into this, and I'm sure there are others doing the same at the same time. It's a mad race, a race to the finish line, that's for sure. So here's what's happening. I took an idea, Nunchuck. Okay, the replacement Nunchucks, the original and all these replacement sticks, use the protocol I2C. And so they are digital devices, data and clock and all that sort of stuff. So they require software to read them and to process them. In other words, this will not work with the PlayStation or the Xbox's X1, X2. The only way that you could even barely get this to work would be to tear this down completely, get at the stick inside, and then hand wire it for this. And that's just not going to do it. And even that may solve the Nunchuck problem, but it does not solve the touchpad, the GlidePoint, and everything else. So, and I hate breadboarding, but I love soldering. And I have put together a proof of concept that, lo and behold, is working. So what do we have here? We have a microcontroller. Now, this happens to be an Adafruit KB2040. This is a board I had on hand. The code will run on pretty much anything. So any Arduino. I usually use Cutie Pies, and usually of those, the SAMD21s. This is only because I have it on hand. This is one of Adafruit's breakout boards for the Nunchuck connector, so you don't have to cut off this connector or do your own wiring. You just get this and plug it in. Normally, for my devices, since they're smaller, I hand solder the points. In this case, I'm using the quick connectors just for expediency. And then you have an output, and the output is a TRRS. Okay, well, what is this? This is the handy part that's required. It is a digital potentiometer. It's a dual digital potentiometer. And the way that these devices work is they're controlled through SPI, the serial protocol. And the microcontroller says, hey, potentiometer 1, which would be X or left and right. Hey, potentiometer 2, which would be up or down, north, south. Go to these settings. These are available in different ranges. This is a 10K range, which is the same range that all of these joysticks are. They're all 10K potentiometers in there. So this is a 10K potentiometer. So I could say, the microcontroller can say, hey, go to the midpoint. Hey, go to left. So it simulates the potentiometer. Like, well, here's one right here for one of my other products, a MIDI product. So you have a potentiometer, just like that, the good old dial, volume control. Well, it's the same thing with joysticks. And what this is simulating that. And it amazingly works out really, really well. So what happens is, in this particular setup, there's code running on the microcontroller that talks I2C to the Nunchuck. So this is a digital serial connection that they're talking back and forth to get readings from the Nunchuck. Then, based on those readings, the same code talks to the digital potentiometer and says, hey, go to this point, hey, go to that point, hey, go to this point. And then those wires go out, the 4 wires, to the TRRS, which then go to the X1, X2 on the Xbox controller, or the expansion ports on the PlayStation 5 access controller. And there's 4 lines here because you have ground, power, and X and Y. So I don't have a PCB or anything made for this, but this is certainly something that I could see a PCB being made so that we can have the chip. This happens to be a different package, which is easy, big, and solderable, but it's also available in surface mount. There are no other components. It's the microcontroller, it's this chip, and wiring. So there are no other things going on, so it should be relatively easy to do a board if I knew how to do that. Hint, hint to anybody out there. So this is great. I've proven out that I can have a digital controller going to my microcontroller, going to the digital pot, out the digital pot, then to the analog line to the controller. And I can't show it to you right now, but as I move this stick, sure enough, the analog stick moves on my test program. So I think this is really exciting. It opens up stuff like the GlidePoint, which is really, really useful for SMA users and will allow those users to use the no tension device with a PlayStation 5. Now, the key thing with the access controller, it can only be configured with a PlayStation 5, which I don't have. And I don't have the controller itself, so I'm testing through the Xbox because they have similar wiring. Once the PlayStation 5 access controller is configured, it can be used with a PC, from what I've heard, but is limited to the number of buttons. So it's really a PlayStation 5 specific solution. And, I won't be doing this for Xbox because there's really not a whole lot of point, because I've got the USB on the Xbox, which gives me more buttons. Even though the buttons are limited, it gives me more. The one situation where this might come in handy is if I need to make a custom trigger controller, let's say for acceleration and brake for a car, where maybe those sensors are not mechanical potentiometers, but are something like Hall effect sensors. Those are magnetic sensors. In that case, I could have the microcontroller read the Hall effect, get what its value is, and then translate that into the trigger analog values that the trigger connections will like. So, long story short, executive summary, I have proven out that this dual potentiometer is working fine, and it'll work with any of these Arduino boards. This one in particular is a MicroChip. It's the MCP42010 series. So it is specifically the MCP42010, I believe, for 10K. They have a couple of them for different ranges. You can get 10K, 50K, and 100K. Since we're dealing with joysticks, it's 10K. If you're wondering about resolution, it has 256 steps per potentiometer, so it could adjust a granularity of 256, which is kind of interesting because the I2C data coming off the Nunchuck is also an 8-bit value, a 256 range. So I actually don't have to do any mapping. What's center here, which is around 127, 128, is center on the digital potentiometer. So that is the one that I'm using, the 10K version. It connects again via SPI. You need the MISO. You don't need the MOSI. You need MISO, clock, cable or chip select. Also, if you're using this chip, important tip, there is a shutdown pin and a reset pin on here. Reset resets to center values. Shutdown puts it in low power mode. You cannot have those floating. Those two in particular have to be held up. So what I do is I attach both of them to a digital pin, and I do digital write high, and that keeps it up. And if I want to reset the device, like I reset it on startup, I pull that pin low for a second, and then I pop it back to high, and that resets it. I'm not using the low power one right now, but if it would work exactly the same way. So talking to this, it's extremely simple SPI. It is nothing weird at all. You hold the cable select low. Normally it's high. Hold it low. Send an address. Send a value. And then release the cable select. And in releasing the cable select, putting back to high is important too, because the value does not actually get set until that cable select goes back to high. So you bring it to low, send your two things, bring it to high, and it's committed. All this happens in milliseconds, so it's very fast. I don't know what the lag is on this, but it's certainly faster than anything I can do. Well, that's a long one, but hopefully an informative one, and we'll move forward with getting more controllers available for the PlayStation access and opening up opportunities for the Xbox adaptive controller when we want to do fancier triggers or other sorts of controllers without having to go through the USB. Still need the microcontroller, still need this, but we could skip the USB altogether. Thanks for watching.